Thank you so much, Emily. And it's an absolute pleasure to be back here in Pasadena. I was actually here at the 2009 Sagan Exoplanet Summer School when I lived about half a mile in that direction. Now I live about 5,000 miles in that direction, but handily, there's also a meeting taking place here on campus about a future flagship mission to Uranus, which I'm really excited to see happen. So I'm collapsing my wave function here in this room for this morning and collapsing my wave function over in the Beckman Institute for this afternoon. So thank you so much to the organizers for inviting me back. And I have the somewhat difficult task of summarizing in 25 minutes all the lessons that we could possibly tell you exoplanet scientists about the solar system. And in fact, I'm going to start with a cautionary note. So back in 1935, a chap called Henry Norris Russell told us planetary astronomers, and those of us fans of atmospheric physics, that the problem of planetary atmospheres, so perplexing in its solution, there we go, so perplexing a few years ago is now far advanced towards its solution. Nearly 90 years ago, this was, we were being told by an astronomer that planetary science was solved. We had done that, move on to the next thing. It's very dangerous then for a planetary scientist to stand up in front of all of you who are starting on your journey to study these distant extrasolar planets and to try to tell you some of the lessons that are learned. One thing I do fully agree with Henry Norris Russell, and this is Henry Norris Russell of the Hertzsprung-Russell diagram, you may have me familiar with the name, who said that both physics, chemistry, geology, biology, and technology, and various other fields all had to come together in the study of these distant worlds, both in our solar system and now beyond. And that's why I'm so passionate about this field. Okay, we're masters of many trades. At least that's why I like to think of these things. I fundamentally disagree that planetary atmospheres was a solved problem in the 1930s. And in fact, if there's one take-home message from this presentation today, is that there is still a heck of a lot about our solar system planetary atmospheres that we're still struggling to understand. And I'm going to dwell on the topic of clouds and aerosols, just as Mark did for the brown dwarfs, as that is still a challenge today in interpreting some of the spectra that we get from these objects. On the planet Earth, we have a single condensable that we need to worry about, water vapor condensing to form clouds. And as you can see in the altitude diagram on the right-hand side, and in these lovely pictures from Met Office users in the United Kingdom, there's a huge variety of different forms of clouds that single condensable can take, distributed over a vast range of altitudes up towards the tropopause level here on Earth. This enormous towering cloud is a cumulonimbus cloud associated with lightning activity and strong precipitation, but you also get stratified cloud layers forming due to condensation at different points in the temperature pressure profile. So that's a single condensable species here on planet Earth that we need to worry about. Move across to the planet Jupiter. So Jupiter, as imaged by the Juno spacecraft and put together by talented amateur citizen scientists, Gerald Eichstadt and Sean Duran doing the image processing here, you can see a plethora of structure in the clouds of Jupiter, these swirling eddies with little, what the Juno team refer to as pop-up clouds, but realistically are cumulonimbus clouds sitting up above stratified cloud layers. Here we have at least 3 cloud decks that are intermixing that we need to worry about: ammonia ice, ammonia hydrosulfide, and potentially water ice, although I'll get onto why we don't see spectral signatures of those in just a few moments' time. But you can see the complexity we're getting here from multiple cloud decks interacting. So clouds on giant planets have multiple different types of composition. And this is a simple equilibrium cloud condensation model that predicts where some of these condensates will be condensing if you assume homogeneous nucleation, i.e. it gets to its saturation point and immediately forms a cloud deck. You can see that it has an effect where when you form a cloud, it will create a small change in the molecular weight of the atmosphere, therefore changing the lapse rate of the atmosphere just slightly. It makes the lapse rate slightly less steep. This has a stabilizing effect on the atmosphere and can actually segregate or separate different regions of atmospheric circulation between the different cloud decks. Now, different condensables will have different sizes of effect on these lapse rates, and therefore you get different a differing ability to put a lid on top of your atmospheric circulation. But nevertheless, condensation can have a stabilizing influence and really change the circulation patterns as a function of height. The other thing you'll notice, if I just go back one, is that the predicted abundances from these equilibrium cloud condensation models have a uniform abundance of the volatile below the cloud base, i.e. you're being governed by a saturation vapor pressure curve up above the cloud base, but below it, you should have a well-mixed abundance as a function of depth. This hardly ever works, and the Juno observations, particularly the microwave observations from the Juno spacecraft, have shown that this particularly doesn't work for ammonia gas. In fact, these are observations that are now several years old, taken by Leigh and the team on the microwave radiometer, which show the distribution of ammonia as a function of latitude and pressure just here. The cloud base for ammonia ice is way up here at about 0.7 bar, and you could see that ammonia is depleted almost everywhere across the Jovian disk, except for at the equator, where we have a strong column of ammonia that may be related to simple upwelling or could be some more complicated processes converging ammonia gas on the equatorial region. But the take-home message here is that the volatile is clearly not well mixed below the cloud base, and something else is responsible for depleting it. Now, my colleague Tristan Guillot and his co-authors have come up with a concept called mush balls. Now, mush balls, you think of them as an exotic condensed phase where you have an injection of water by powerful convective upwelling. That water will then trap the ammonia gas that's high up within the atmosphere, form a kind of mushy hail, which then falls out to great depth, taking the ammonia gas with it. And that falling of the ammonia gas is their suggestion for why you get the depletion at certain locations. There is a slight snag in that in order to get this depletion everywhere on Jupiter, you need powerful convection to be happening everywhere on Jupiter with this mushball hypothesis. So I think there's still quite a lot to be worked out with that. But nevertheless, the planetary community is wrestling with this idea of how do you get this enormous amount of depletion down below the cloud base? And then why does it around about 60 bar start to show this, this uniform distribution again? Nevertheless, a puzzle still to be solved. The next theme I want to talk about is that whenever we look at giant planet atmospheres in particular, disequilibrium is absolutely everywhere. Now, these atmospheres are primarily made of the most cosmically abundant elements across the solar system. So hydrogen and helium dominate in the 90% level, but then there are small smatterings of carbon and oxygen, nitrogen and sulfur. And all of these are found in their reduced and hydrogenated forms because of the amount of hydrogen that is present. So we get volatiles like methane, ammonia, hydrogen sulfide, and water. They then go on to condense to form the condensation clouds, and of course influencing the chemistry by sequestering volatiles down below the cloud bases. And if you have a volatile that sits around up at high altitudes, such as methane, photolysis, UV photolysis by photons from the sun, splits that methane molecule apart and initiates the rich chain of hydrocarbon chemistry that Julie was talking about on Monday. And these upper atmospheres of all four giant planets are like chemical factories. We see huge numbers of different hydrocarbon species, up to C6 species. Benzene has been discovered in all four of the giant planet upper atmospheres. We also have external processes to mix into this as well, because we have things raining in from outside, be it large cometary impacts or smaller scale interplanetary meteoroids coming in and delivering their oxygen-rich species into the upper atmosphere that then interact with the methane photochemistry to give a soup of oxygenated species up in the high atmosphere too. But all of this is made even more complicated by disequilibrium. We have mixing from down in the deeper layers that bring gases up into the upper troposphere where we can detect them, but where they have no right to be without this mixing taking place. Mark has already talked about carbon monoxide, which is a classic example of this on the giant planets. Another good example of this is phosphine gas. Phosphine should be sequestered by water chemistry down at thousands of bars, but we see plenty of phosphine on Jupiter and Saturn. In fact, we see it elevated in regions where we think the mixing is strongest. So upwelling is bringing phosphine up to the cloud decks where we can detect it. Similar is true of things like arsine and germane. And because it's so cold, we can also use the spin states of hydrogen, the ortho to para distributions of hydrogen, to tell us something about the circulation patterns within these giant planets' atmospheres. But bottom line, disequilibrium is everywhere, and without it, we would not be able to reproduce the spectra of the giant planets that we see. Mark touched on this a little bit, but this is something that largely is still ignored by people like me, an observer just trying to fit data, and that's the microphysics of these aerosol layers, okay? We rely on our modeling colleagues to come and tell us that the numbers that we're getting back from our retrievals are sensible or not, and usually it's the or not part of that, that caveat, okay? Because you can see this is a diagram I stole from a terrestrial meteorology textbook, which just shows the range of processes that might be occurring within a single cloud as the particles grow under various different types of conditions. They freeze, they then rain out and collide with other particles. This is a very complicated system that for solar system observations, we typically ignore when fitting the data that we have so far. So to give you an example of where we are today, I think, with understanding some of these planetary atmospheres. My colleague, Pat Irwin at the University of Oxford, who was my PhD supervisor, he's been studying the ice giants for many years, and he's been trying to do what many of us have shied away from for a long time, and that is to fit data from multiple instruments across as broad a spectral range as possible to come up with a cloud scheme that fits everything. Okay, it's not perfect, but it does reproduce all of the data rather than focusing on a little narrow sub-range of the spectra and assuming that that is giving us the right answer. So what he's come up with is something that relies on the raining of cloud condensation nuclei down from the photochemical domain to seed the clouds at deeper levels. So photochemistry produces things like hydrocarbon ices. They then sediment downwards, would seed a methane cloud layer that almost immediately then snows out, bringing those cloud condensation nuclei even deeper down, where they're then able to seed a H2S cloud, which we think are the main primary cloud decks on Uranus and Neptune, and seed a layer at around about the 2 to 5 bar region, which makes most of the opacity of Uranus and Neptune when you observe it in the near infrared. Now, this could all be wrong, okay? This is one solution based on a retrieval model that reproduces the data at the moment, but as soon as we start changing our assumptions about the aerosol opacity, about the scattering properties of these aerosols, about the shape of these aerosols, because typically we will assume spherical particles still, which we know from terrestrial observations is not necessarily a good assumption, this could completely change. But this is the best that we have today. And you'll notice the importance of having those cloud condensation nuclei being delivered to certain altitudes to form the cloud decks that we get. Now, what I'm touching on there is that whenever we look at solar system spectra, to this day, the solutions that we get are degenerate and dependent upon some of our prior assumptions that we put in. You must always, always, always test the sensitivity of your solution to the priors that you're putting in to that retrieval model, because otherwise that retrieval model can take you into a local minimum of goodness of fit that might be completely irrelevant to the target that you are looking at. I put together, as best I could, all of the different wavelengths that we have observed Jupiter in over the past 40 years or so, all the way from the ultraviolet here on the top left, which shows scattering from upper atmospheric hazes, through the reflected sunlight visible domain, which has these big absorption features due to methane. That's how we can sound different altitudes within the Jovian atmosphere, through into the near infrared domain, where these methane absorption features continue, but we start to see emission from the ionospheres, particularly H3+ just here, and to the classic 5 micron window, which is shown on the right-hand side just there, where we have a window that's carved on one side by phosphine absorption and on the other side by ammonia absorption, and allows us to see down into the cloud-forming region of Jupiter. And what you see there on the right-hand side is clouds appearing in silhouette up above the brighter, deeper 5-micron emission that's coming from the deeper, warmer atmosphere. So beyond 5 microns, we get into the thermal infrared domain just there. So this is that same 5-micron peak just scaled, where you can see methane, and then all of the different products of methane photolysis, in addition to phosphine and ammonia absorption features. Finally, beyond about 15 microns, we get into a lovely, smooth hydrogen-helium collision-induced continuum, which is our thermometer. If we assume we know how much hydrogen and helium is on the giant planets, which, spoiler alert, we don't know for sure, we can then measure the temperature. Okay, we use this as our thermometer to measure the 3-dimensional temperature structure. But still, fitting these data is an enormous challenge and remains degenerate to this day. Okay, I want to show you now where this is, I want to say cutting edge, okay, but this is my work, so that sounds a little bit like blowing my own trumpet. This is James Webb Space Telescope spectroscopy of Saturn. This is not published yet, so please don't share it. We basically placed the MIRI integral field unit spectrometer, and that's the size of the footprint, at 4 places, 3 on the Saturnian disk and 1 over the Saturnian rings, to measure the spectra of this object. Why are we still doing solar system science with the James Webb Space Telescope? I hear you all cry as you want to get exoplanetary data. It's because there are regions of giant planet spectra that we had not got access to, even with missions like the Cassini spacecraft or the Juno spacecraft, okay? There are regions of the spectrum we have not seen. This region between 5 microns and 7 microns, for example, has never been spatially mapped on the giant planets, because strangely, instruments would stop at 5 and start again at about 7.5. The data is in blue and red for 2 different latitudes, and the model fit with an optimal estimation retrieval algorithm is shown in black. We're pretty happy with this model fit, okay? Now, unfortunately, this means we actually understood the atmosphere pretty well already, because there wasn't too many tweaks we had to make here. However, we need to include multiple scattering of reflected photons in order to do this. If we don't include multiple scattering of reflected photons, we cannot fit this region of the spectrum. And as soon as you're talking about multiple scattering, you have to worry about the refractive indices of the particles that are doing the scattering, the size distribution, the shape, and it gets really complicated really fast. There are so many dials that we can turn in our retrieval algorithm that you can always get a good fit, but you're not confident that good fit is realistic. Again, test the sensitivity of your retrieval results to the prior assumptions that you have put in. Now, thankfully, with this particular retrieval model, I found I needed to have 2 cloud decks. Sorry, I'll point with a pointer. 2 cloud decks, and those 2 cloud decks are consistent with a lot of the work that we've done with the Cassini spacecraft over the years. And I won't get into the details, but they show some very interesting seasonal asymmetries, changes since the end of the Cassini mission, and it's teaching us a lot about the chemistry at work within Saturn's atmosphere. Now, that model, I tried to use an Occam's razor approach. I used very, very simple assumptions about the size distribution and about the refractive indices. The refractive indices are controlled by the composition of the ices. So if you choose ammonia ice, you'll get big absorption features in your refractive index data. You choose NH4SH, which is the next logical choice for Jupiter, you get big absorption features in your refractive index data. But it's very, very rare to see absorption features from these ices on the giant planet. Ammonia ice and water ice are only ever seen for fleeting instances in regions of very powerful upwelling and convection, so fresh clouds, if you like. In fact, in 2010, we had a lovely storm eruption on Saturn that brought up fresh ammonia ice and water ice that Larry Sromovsky did some fantastic work fitting that data set to show that it was present within the Saturnian storm. Kevin Baines, over 20 years ago now, used Galileo data to show that water ice signatures and ammonia ice signatures were only present near the Great Red Spot, where jet streams are crashing into one another and powering this turbulent convective activity. So we hardly ever see signatures of the ices or the condensates that we expect. They're always masked, they're always invisible to us. So what's doing the masking? Well, the go-to answer for this is some kind of photochemical coating of those fresh aerosol particles, giving them the colors that they have, which is still a mystery to this day, but masking and hiding those pure spectroscopic signatures. So I just wouldn't go looking for them on Jupiter anymore, because we're not going to see them, because they're masked by the chemistry. And I've got two examples here for Titan, where you have hydrocarbon chemistry forming aerosols that would then sediment down and coat aerosols at deeper layers. And of course, Titan has a fantastic methane cycle where you get methane rainstorms raining down onto the Titanian landscape that then flows into rivers and into seas, and we've detected seas, and that's a whole lecture all by itself. Titan is an absolutely fascinating body to explore. But photochemistry is potentially coating these condensates. Another example going into the inner solar system now with Venus. So the hydrogen, the sulfuric acid clouds of Venus are formed via a chemical reaction. Okay, we understand that fairly well, and you get rain out towards the surface, but of course Venus is so hot it evaporates again before it ever gets down there. This is that process called Virga that Mark was mentioning earlier on. But above those sulfuric acid clouds, we have all these dark patterns and features that you can see in this lovely image from the JAXA Akatsuki mission. We don't know what that UV absorber is that's causing that dark colors, okay? It's some chemical component that is clearly localized at certain latitudes by the dynamics of the super rotating Hadley circulation of Venus. And nevertheless, to this date, we still don't know what that UV absorber might be. And the best example I can think of is this, something from my own research. To this day, after 40 years of exploration of Jupiter via spacecraft and ground-based facilities, we have no idea what is making the Great Red Spot red. Okay, we know it's a very good blue absorber. That's a tick. But there's plenty of very good blue absorbers that it might be. This is a gigantic swirling anticyclone. It's got a peripheral jet that we think entrains the air within the vortex. You keep that air within the vortex for a long period of time, it's being cooked by UV photolysis, and that may be leading to the production of this red chromophore. But think of it as like a haze, a lid over the top of the Great Red Spot that's an orange or red filter that's sitting above all the dynamics deeper down. And in fact, this cartoon from my colleague, Mike Wong, shows that the Great Red Spot, it's like a big pancake-like structure. It's much wider than it is deep, but it does have structure with depth. There is what we call a midplane, where the anticyclonic circulation is strongest, the jets are strongest, but then those jets weaken with height and they weaken with depth, and that gives you a sort of twofold structure to these big anticyclones, where you have a midplane with a warm core below and a cold core high above. But there's still a lot to be figured out about these meteorological patterns. Now, that gave you an idea of what happens with depth. And the Juno mission is doing a great job at showing that atmospheric layering is really important, okay? The environment changes as a function of altitude as you go down through the atmosphere. So I won't get into all the details here, but you can see that the contrast that we measure above Jupiter's water cloud on the left-hand side changes and flips from dark to bright as you go down deeper below the water cloud. There are different circulation patterns above and below the water cloud, segregated potentially by that change in the lapse rate that we saw from the equilibrium cloud condensation models. And even deeper, Juno has revealed that the winds of Jupiter go down to about 3,000 kilometers of depth. Contrast that with the 70,000 kilometer diameter of Jupiter, and then they die away to a region of calm down at depth, which may be related to the transition from molecular hydrogen into metallic hydrogen, that bizarre exotic soup of matter that makes up the bulk of the atmosphere of Jupiter. So summary so far. Is that I'm over 25 or I'm at 25? I have 1 minute left. So condensates with one are very complex. Multiple condensates can cause very interesting distributions within a planetary atmosphere. Equilibrium cloud condensation models fail to reproduce what we see. There are other processes at work. Spectral retrievals, even in the solar system, are highly degenerate, and you must always test your sensitivity to priors. Photochemistry is key to probably understanding the spectra that we see, and the environment changes with altitude. Depending on what altitude you're seeing, things will always alter. But that's not all, because all of this changes with time. And in the final 38 seconds, I will say that Mars has a cloud and dust cycle, cycling between dust storms with water clouds and carbon dioxide clouds, forming and changing every time we go and look. Neptune's clouds change on a daily scale. We don't see the same cloud on Neptune from night to night. Uranus has a seasonal hood of reflective aerosols over the northern and southern poles, which changes on seasonal timescales as observed by the Hubble Space Telescope. Saturn has seasons and seasonal storms that erupt and completely change the thermal structure and the reflectivity of Saturn on a periodic basis. And Jupiter has weird cycles of atmospheric activity that change from year to year to year and don't appear to be connected to any sort of seasonal timescale that we understand. So if I just go to I'm going to go and finish actually on this slide. We now have a new eye on the solar system, the James Webb Space Telescope, which is going to reveal new insights into a lot of these fundamental phenomena that we're still struggling to understand. And this, even in the first cycle of observations, we've seen absolute wonders from JWST. So here's to that continuing for many years, if not decades to come. And I think that's a good place to end. Thanks very much. I was very nearly at the end. I just wanted to leave there.
Hi, my name is Rosario. I am very interested in like gas giants and also their very active moons. So my question is, has there been any research or studies done on the interaction between these gas giants and their active moons and how it may influence, or there's like a dynamic going on there?
So the audio is really bad at the front.
Okay.
I think you said interaction between the giant planets and the moons. Was that
Yeah,
right?
so like active moons like Enceladus or Io on its gas giants. Has there been any studies related how there might be an interchanging reaction between
Absolutely,
them?
that's a great question. And in fact, the coupling between the central planets and their wider system, whether it be rings or active satellites, is an active topic of exploration today. The best example I can think of is the material that's flowing inwards into the Jovian and Saturnian atmosphere from their active moons. Water, in particular, seems to be raining down at particular locations within the Saturn's atmosphere from Enceladus. But it's interesting because it connects to the magnetic field. Okay, the water doesn't just flow radially inwards, it flows along the magnetic field lines because I presume it's charged in some way, and then enters the atmosphere at magnetically conjugate latitudes to where the moon is sat within the magnetic field. So it's all one big coupled system, and certainly an active area of research.
Hi. Okay, there we go. I actually had a question with Saturn. Since you talked a lot about Jupiter's red spot, and since James Webb kind of looked at Saturn also, do you think we'll start to learn more about the Saturn hexagon?
The Saturn hexagon. Now, I planned the Saturn guaranteed time observations, and it was supposed to happen in 2019. And at that time, we were at the height of northern summertime conditions on Saturn. So the hexagon was right there in view with the central polar cyclone glowing nice and warm. We'd studied it for several years with Cassini. And then there was a 3-year delay to JWST. So the observations that I showed you there, we actually pushed them to take it as fast as possible because the hexagon is receding from view. And if we did it now, you wouldn't see the hexagon anymore. And in fact, it will now be I think if I do the maths right, it's the 2040s before we get another glimpse of the hexagon. So we won't learn any more from spectroscopy and observations, but models still don't quite reproduce it. And I think the next generation of models will really start to answer questions of, is it shallow? Is it deep? Is it connected to the interior? How did it form in the first place? Why has it been there so long? These are modeling questions rather than observational questions.
Yeah, one of the hottest topics now in exoplanet is to understand the nature of the sub-Neptunes. What is your opinion? What should we learn about Uranus and Neptune that could be applied to our understanding of these exoplanets?
Oh gosh, that is a great question. I think, so obviously we want a mission to Uranus and Neptune. That's why I'm here at Caltech at the moment trying to do it. And I think one of the key things that we could only do via mission rather than doing it remotely is understanding the interior density distribution of these ice giant class of worlds. We understand it fairly well for Jupiter now with the Juno mission. Cassini gave us some good ideas for Saturn, but Uranus and Neptune are fundamentally different objects to Jupiter and Saturn. And we don't know what sort of the phase transitions are as a function of depth. Do we get this super ionic layer of water? Are these really ocean worlds in a classic sense rather than giant planets? And I think if we can constrain that for Uranus and Neptune, then as you are all looking out at sub-Neptunes and objects of similar sizes, you might have a better starting point for interpreting what the insides of these worlds are like from the atmospheric spectra you're measuring. Okay, thank you very much, everybody.
Yeah.